All right, take 4. So video is crapping out. This was going to be the video part 2 of, and you're going to be able to see it that way on the YouTube. So watch part 1, it's about 20-30 minutes. I think it's 30 minutes. And then this will be part 2. So I'll restart what I was explaining at the end of the last video. Basically what I said that I would do is I would make the PT, VT, and AT graphs of all these little word problems. Once I can hopefully get these videos to work, I'll upload them and then you guys can see them before the test. Alright. Okie doke. So I'm going to go through 3 of these problems. I'm going to go through these first 3 problems and we're going to do PT, VT, and AT graphs for all of them. And the way I'm going to draw it is I'm going to draw them adjacent, right? And what I mean by that is I'm going to draw them right next to each other and with the same t-axis. All right, so here's my PT, VT, AT. Okay. And I made them the same width like this so that you know that whatever is happening at this time on the position graph is the same thing happening at this time on the velocity graph, is the same thing happening at this time on the acceleration graph. So this is a car that's stopped at a light. All right, so that means if it's stopped at a light, that means its original velocity is 0. The origin, I said, is the intersection, and you start at the intersection, so your position is 0. And your acceleration is going to be constant. We only deal with problems that have constant acceleration. So the acceleration is a positive constant because you press on the gas and then you accelerate, your speed increases. Based on that, and knowing that the speed increases, I know that my velocity is going to be increasing, right? Because I'm going away from the origin, and therefore my velocity is going to be going towards the positive, and I'm gaining speed. And at any moment, if I take the slope of this line, the slope here is going to be equal to my acceleration constant there, no matter where I look at the slope, because it's a linear curve. All right, and because the velocity keeps getting faster and faster and faster, at each time interval, I'm going to be doing more and more distance. So it'll look something like this, right? And if you, and it starts at 0 actually. And if you extend it into the imaginary negative time, it should actually kind of look like this. And this is a happy face parabola. And if you're familiar with the quadratic function, the y equals ax squared plus bx plus c, you know that acceleration is positive because you have a smiley face quadratic function. Alright, so this is what the acceleration, velocity, and position graph would look like for a car that stopped at a light. So it's stopped at a light, it's this the origin, it accelerates and speeds up, so the position's changing, velocity is changing, starts from a 0, and acceleration is constant all throughout. Alright? So let's do the falling object, and this falling object is falling off the top of a building, obviously. So let me just draw the 3 graphs. So this is this problem here, is the falling object from the top of a building. Here's my position, here's my velocity, and here's my acceleration graphs, and they're all as a function of time. And so the position, the original position, is at the top of a building. And it's falling off the building. Boom. Like that. This is PO, which is a positive value, which we mentioned here. Velocity, because we're just dropping it, starts at 0 and then goes downwards like that. And acceleration is constant and it's always negative 9.8 meters per second squared. All right? Very straightforward here. And here, because my acceleration is negative, if I were to draw this imaginary quadratic function, you would see that I have the upside down smiley face, because if I have a negative in the y equals ax squared, if I have a negative a, then I have a upside down or a sad face. Okay? Alright. Now finally, we have this one, which is the most complicated one. And I hope that once we do this, you understand a little bit about the relationship between position, velocity, and acceleration. So here's my position. Here's my velocity. And here's my acceleration. And so what's happening here is that you're on top of a building, so your position, your original position is way up there, and then you're throwing an object upwards. So what's happening is right away, right after the toss, your object is actually going up and then down. All right? And I'm going to draw a little imaginary line here that's going to go all the way down here. And hopefully that'll help you a little bit with what's actually happening. So if I'm throwing something upwards, that means my initial velocity, my VO, is going to be positive, right? And it's going to decrease. And then when the position of the object hits its peak, my velocity is 0. That's when it intersects the timeline. And then it becomes negative. So everything after here, the velocity is negative. Similar to here, everything after that point, the velocity is negative. All right, so here it's going towards the origin, towards the negative numbers. So my velocity is negative. And we know that because if we look at the velocity versus time graph, it's all below this axis. And acceleration, because it's constant, is always going to be the same no matter what, negative 9.8 meters per second squared. All right, so it's important to know that time here is the same as time here, right? And position and velocity are very closely related, and you can tell a lot of information about what the object is doing just based on this graph like this. Now, if I throw you a little curveball tomorrow, or Thursday rather, on the test, and I break it up into a problem that does multiple things, like for example the one in the Kinematics problem 8 where there's a penny who drops from the building and then snags a flagpole and then restarts its velocity. Like, don't let that kind of stuff throw you off, really, because what you just need to do is break it up into the different parts, because it's never going to get more complicated than breaking it into problems like these. Right? And if you can do this once in a problem, you can definitely break it up and do this twice or 3 times in the same problem. It always comes down to doing this kind of routine, making a graph, figuring out which formula to use or which graph to figure or which areas to calculate. It always comes down to the same calculations. I hope this tutorial was helpful. If it wasn't, then continue studying the way that you were doing it before. If it was helpful, then great. Ask me any questions if you have any. You can email them to me. I know that you guys are going to be stressing out for the test on Thursday. I don't want you to be stressed out because it's going to be a relatively easy test. But if you are stressing out and you need to ask questions, I'll be checking my emails pretty regularly on Wednesday night. So don't worry about sending those my way. All right? So good luck and have a good night.